Hello everyone, today we are going to introduce the comparison between Bayesian statistics and classical statistics. First, let me introduce this topic to you guys through an example. We all know that when we're flipping a fair coin, the probability of getting a head is 0.5. But why is the value 0.5? Well, the classical statistics says we can toss the coin for 1,000 times and let's say we get 491 heads with 509 tails. So the probability of getting a head is approximately 0.5, which makes perfectly sense. However, often the case is that we don't have the chance to toss a coin as many times as 1,000. So possibly we only toss it 5 times, and all 5 times are heads. Does this mean that the probability of getting a head is 1? Definitely not, because we have the prior knowledge of flipping a coin that the probability is more likely to be 0.5 and very unlikely to be 1. So this is the idea of Bayesian statistics. As two different branches of statistics, classical and Bayesian have a lot of similarities and differences, which we will further discuss below. And this report mainly contains two parts. One of them is Bayesian and classical estimation, and the other part is Bayesian and classical prediction. We also like to introduce an example 1, which will be used throughout the report, which is we toss a coin for n times, and we get each head. P is the probability of getting a head. First, let me introduce the Bayesian and classical estimation. In this part, we only focus on the point estimation, and the interval estimation will not be included. For classical estimation, there are two estimators to be used. One of them is method of moments, also known as MOM estimator, and the other is maximum likelihood estimator, also known as the MLE. Both of the methods, after applying some data, give the result of h over n. And for Bayesian statistical estimation, we first need to introduce a prior distribution, which stands for our prior knowledge of the parameter of interest, which P, of course, for example 1. And for simplicity, we will use the beta 11 prior for this example, which is a uniform distribution. And after applying the data to the prior distribution, we will get our posterior distribution, which is this. And having this distribution, we can use two estimators to estimate the P. One of them is maximum or posterior estimator, and the other is conditional expectation estimator. After some calculation, MAP gives the estimated value of h over n, and CE gives the estimated value of h plus 1 or n plus 2. Comparing the two estimations processes, we can see that classical estimate is a point estimate based solely on the sample data, while the Bayesian estimate is a summary of the posterior distribution that takes into account our prior beliefs as well as the data, of course. And comparing the results, we can learn something interesting. For classical estimation, we got two results, and both of them is h over n. However, for Bayesian statistical point estimation, we got two different results. One of them is h over n for MAP, and the other is h plus 1 or n plus 2 for CE. So we can see that the result of the Bayesian estimation is affected by not only the prior belief and data, but also the choice of estimator. And also, it is possible for Bayesian and classical estimation to give the same result. For MAP estimation in Bayesian, it's only because that we set the prior distribution as a uniform distribution that it gives the same result as the MLE in classical estimation. But it's not the case for CE estimator, because only when the sample size is so large that the influence of the prior distribution can be neglected will the CE estimator give the same result as the classical ones. So in conclusion, the choice between the two methods and the choice of specific estimators ultimately depends on the researcher's goals, available data, and most importantly, the prior knowledge. Then next, let my partner Dong-Yi to introduce the prediction part.
So, in this section, we will compare Bayesian prediction and classical prediction. Classical prediction forecasts future events or outcomes based on historical data and statistical analysis using classical statistical methods. The model specification step and estimation of parameters we have already mentioned above. So we focus on using the model and estimator to predict future outcomes. Take the example 1 for example. It's a binomial distribution with estimator p is equal to h over n. And k is the number of hands in predicted events. Assume there's a game where people usually get more than 2 hands in 5 flips to win. So we can have the p function. If we have 2 hands in 4 flips before, and the estimator should be p is equal to 1 over 2, then we can solve the p win is 1 over 2. Similarly, we can use the estimator and the PDF of binomial distribution to calculate the variety of probability in the same way. For the Bayesian prediction, instead of using a probabilistic model, Bayesian prediction combines data with prior distribution and obtains the posterior distribution. Then we can use the posterior distribution to flexibly predict the outcomes. First, we list the equation we need and do some simplification steps. Event A is any event that we want to predict. It's very simple simplification. In this step, we delete x because event A and existing data x are independent. Given explicit definition of A to facilitate our calculation. In the following 5 flips, we will get 4 hands. And for calculation purpose, we define existing data at 4 flips and 2 hands. In section 2.2, we have got its posterior distribution as follows. It's a better distribution. Apply it, we have the result 5 over 28. We notice upper bound and lower bound on the integral change because the probability take value from 0 to 1. And in section 2.2.1, we have got a MAP estimator. Apply it, we can have the result 5 over 32. It is different from using the posterior distribution. And in section 2.2.2, we have got another point estimator, C estimator. Apply it, we can have the same result, 5 over 32. Using different estimator gives the same prediction results, because in the event A on the example 1, we have theta CE is equal to theta MAP is equal to 1 over 2. The calculation of event A above is interesting. The predicted result by using the posterior distribution is different from using point estimators. This is an intuitive and reasonable result because posterior distribution takes the complete information about parameter uncertainty into consideration, while point estimation just uses a single estimator. The results of both point estimation prediction methods are same because the MAP and CE estimator happen to be identical. This is a special case that will happen when the expectation of the posterior distribution is equal to its maximal value. In conclusion, classical statistics assume that the parameters of problem models are fixed and focus on using frequency to estimate probabilistic and thus predict the outcome. In contrast, Bayesian statistics view the parameters of interest as random variable and incorporate prior belief into the analysis. The prior belief will be updated by observed data and then serve as a posterior distribution to make inferences about outcomes. Both approaches have their strengths and weaknesses. Choose which depends on the nature of the practical problem and the available data we observed.